Good afternoon. Today we are going to be focusing on my science project, which I entitled Meteorites and Me. I want to apologize ahead of time for the small screen that we have to work with, but because of the corona lockdown, this is the only screen that I have access to. So we're going to do our best to make this something we can work with. What got me interested in this particular project is this crater right here. If we can move in a little bit on that, that is a picture of the Barringer meteorite crater in Arizona. The Barringer meteorite crater, if you can see, it's got a tiny little building there. That's a road leading up to it. The Barringer crater has a diameter of 1,200 meters. So that's diameter from side to side through the middle, 1,200 meters, over a kilometer in diameter. That's an incredibly large meteorite impact crater. So that gets me thinking about how this might be something that we can recreate in our lives, and do it in a science experiment format. So the hypothesis that we're going to be exploring here in this experiment is: what effect does the height of a ball dropped into a pan of sand have on the size of the crater created by the impact? So we're going to be looking at some key terms here in just a minute, but let's take a look at the outcome statement. This is my prediction of what's going to happen. And my prediction is that the higher the ball is from the pan when it is dropped, the larger the size of the impact crater will be. Now, for purposes of the experiment, I'm going to be measuring the impact crater size by diameter, but as a little bit extra, because I want to work some math into this. You and I are also going to focus on how we can turn that diameter into a circumference, and we'll talk about that in just a moment, but that's a real easy formula as well. So, what's the science concept that we're examining in this experiment? So the main concept that we're going to be focusing on is a physical science concept, which is the concept of kinetic energy, which is what we call the energy of motion. And in this case, we talk about how the kinetic energy of an object is changed by the effect of gravity. Now, I didn't put this here, but it's also pretty obvious from the label, or from the title of this experiment, that another science concept that touches very closely with this experiment is Earth-space science, that of meteorites. So you may remember that a meteor is a foreign object that is traveling through our atmosphere. We might see it as a shooting star because the friction of it entering the atmosphere causes it to burn up and it incandesces. But sometimes the meteor is big enough that a piece of it survives the burn up and it lands here on the planet Earth. That's a meteorite. When it hits the ground, it becomes a meteorite. So let's talk a little bit about the key vocabulary for this experiment. Dustin, if we could just move in a little bit closer to these vocabulary words. The first word I want to talk about is kinetic energy, which we've discussed in class. That's energy which a body possesses by virtue of being in motion. So in this case, where is the motion coming from? In our case, the motion is coming from gravity. It's the pull of gravity. The next word I'd like to look at is impact. And that's the action of one object coming forcibly into contact with another. In our experiment, we're dealing with an impact between two objects. We're dealing with the impact between a marble and a pan full of sand that marble's going to come into contact with. The next vocabulary word is crater, which is a large bowl-shaped cavity in the ground or on the surface of a planet or moon, typically caused by an explosion or the impact of a meteorite or other celestial body. So we've talked about craters on the moon, and I just showed you a crater on planet Earth. We're going to be making craters ourselves, but they're just going to be a lot smaller. Finally, a couple of math terms I want to include are diameter, which is a straight line passing from one side to the other through the center of an object or figure, especially a circle or sphere. So when I measure the size of these craters, I'm going to be mostly focusing on the diameter, which is, again, from one side through the middle to the other side, how much space that takes up. But we're also going to touch base on circumference, which the internet defines as the enclosing boundary of a curved geometric figure, especially a circle. So what that means for us is basically if you were to walk around a circle instead of walking straight through the middle of the circle, how far would that be? The last thing we're going to do with this experiment is we're going to convert the diameters of our craters into circumference of the crater. So how does this science concept apply? Well, we're going to talk about how we can demonstrate that a weighted sphere, in this case it's a marble, it weighs about 15 grams, or excuse me, 0.15 grams, gets kinetic energy from the force of gravity upon it. So when I let it go, its potential kinetic energy turns into realized kinetic energy, and it falls because of the force of gravity. The higher up the sphere is, the more energy it will accumulate before it's stopped by the sand. So what are our variables? The manipulated variable in this experiment is going to be the height of the dropped sphere, the height of the marble at the moment when I release it. That's the manipulated variable. That's what I will be changing myself. And that's also known as the independent variable. The responding variable or dependent variable is the size of the impact crater, judged by diameter and by circumference. So in other words, I am expecting that the size of the impact crater will change. It will be dependent on the manipulated variable or independent variable of the height that I drop it. The constants in this experiment are the amount and type of sand. I used about 1.5 kilograms of sand, and the weight of the sphere, which we will go into for right now, actually. The materials required for this project are going to be an empty dish to contain the sand. I used a baking dish like you might find in your kitchen. Your mom or dad might have one. I used about 1.5 kilograms of landscaping sand. This is the sand that you can buy at a landscaping department of a department store like a Walmart. Or if you live by the beach, you can just go to the beach and pick up some sand. And I apologize, I made a mistake here. My marble weighing about 0.15 grams, not 15 grams. I'll have to fix that in the final version. I used one roll of measuring tape for drop height. You can see the picture here. I've got my measuring tape extended. I used a ruler to measure the crater diameter. And then I used a paint scraper to smooth the sand between drops because I want a nice, smooth sand platform for the marble to fall into. So here's just some pictures of me in various different stages of the experiment. It's hard to tell from this picture on the left because it's a kind of a high up picture, but there is an impact crater right there that I am measuring the diameter of. And if we move over to this picture on the right, that's just me smoothing down the sand in between drops because I don't want my marble to hit an area that has already had an impact crater in it. And that could skew the data. That could make it look like the impact crater was different than it actually was. So here's the procedure that we follow for this experiment, and it's pretty simple. Step number one, you put about, again, I used about 1.5 kilograms of sand into a wide flat baking dish. You can use whatever amount works for you, but I recommend that you have a nice thick layer of sand, maybe 3 centimeters thick, so that your experimental data isn't skewed by the weight of the marble hitting the pan beneath the sand. So you want a good amount, 3 or 4 centimeters of fine sand in there. You smooth the sand completely flat with your paint scraper or whatever that you're using. Again, I mentioned that before. We just don't want to have... we want our data to be showing the results of the drop of the marble and not much else. So we don't want it to show the results of what happens when you drop a marble in a big old clump of sand and next to it there's a big divot in the sand. We want it all to be nice and flat. I started by extending the measuring tape out to a length of 10 centimeters. And then when I held the marble up at 10 centimeters, I just dropped it into the sand. And then I used my ruler to measure the diameter of the impact crater. And then you're going to want to take data many, many times. So I noted that my independent variable in this case was my drop height, and the resulting dependent variable was my crater size, and I wrote them down. I actually put them in an Excel spreadsheet, but you can write them down or you can put them on a PowerPoint, however it works for you. And then I recorded another 9 drops at the same height, that's 10 centimeters, and I recorded as I go. So that was a total of 10 drops at 10 centimeters of drop height. And next, I added an additional 20 centimeters of drop height to the measuring tape so that I was now dropping the marble from 30 centimeters of height. And I repeated the steps I did before. You smooth the sand flat after the drop. You drop the marble in, you measure the diameter, and then you do it again. Finally, I added an additional 20 centimeters of drop height for a total of 50 centimeters of drop height, and then I did it 10 times to get a good amount of data to work with. This is the data I ended up with. The drop heights are represented here. My manipulated variable is my drop height. My dependent variable or my resulting variable are these diameters here. I measured in centimeters. I've got my total here. So in other words, the total amount of diameter created by impact craters at 10 centimeter drop was 22.1 centimeters, 26 centimeters at a 30 centimeter drop, and 28.1 centimeters at a 50 centimeter drop. Now remember, this is the total. I added all these together. I get the mean by dividing these numbers by the number of drops, which is 10. 22.1 becomes roughly 2.2 when divided by 10, and so on. And then I've also got my median, which is the amount directly in the middle of those 10 drops. It was 2.25 centimeters at a 10 centimeter drop, 2.6 centimeters at a 30 centimeter drop, and 2.8 centimeters at a 50 centimeter drop. Mode is what showed up the most times. So for my 10 centimeters, I had an equal number of 2 centimeter measurements and 2.3 centimeter measurements. For my 30 centimeter drop, I had a 2.5 show up the most. And for 50, I had an equal number of 2.8 centimeter and 3 centimeter drops. Finally, the range is how big is the difference between the smallest diameter and the largest diameter. In this case, it was 0.5 centimeters at 10, 0.3 centimeters at 30, and 0.5 centimeters at 50. Here's a very simple bar graph showing the average size. Again, that's the mean in this case. The mean of the drops that we did. So we can show that the 10 centimeter drop had an average smaller size crater. The 30 centimeter drop had an average larger size crater, and then the 50 centimeter drop had the largest average size crater, which does match my predicted outcome. So this is, again, just a recap of the data that I just talked about. So it does show, this experiment, that there is a direct connection between the size of the impact crater and how far the sphere or the marble was dropped before it hit the sand. Now, there is an upward limit as to the amount of kinetic energy that marble can put in that sand, and we call that terminal velocity. Now, I did this inside my house, so I didn't have a ladder high enough to reach terminal velocity, but within the atmosphere of the planet Earth, there is a point where things can't drop any faster because the friction of the atmosphere is going to keep them from accelerating any further. However, we didn't get there with this experiment. A real-world application for this would be the connection between kinetic energy and impact crater size is the sort of thing that you'd be used by engineers. It might be used by people who are developing cars. They want to know how much damage is being done to a car in a crash test. If you crash this car at 30 miles per hour, if you crash the car at 50 miles per hour, if you crash the car at 80, they're going to be able to take this sort of information about the correlation and even the causation between the kinetic energy and the effect of that kinetic energy when it stops. We used crater size, but the same physics applies to other things besides craters. My narrative diary, I'm not going to go over too much right now, but because I want to talk to you a little bit about how we're going to turn this information from the diameter of the crater to the circumference of the crater. So we're not going to be walking around our tiny little craters because they were very, very small. But this is the sort of map that you'd use if you wanted to walk around that Barringer impact crater in Arizona that I talked about, and you wanted to know how far you'd be walking if you walked around it. So let's just talk about first what the diameter is. From one side of the crater to the other, down the middle, is going to be our diameter of the crater. And you saw a picture of me taking a measurement from the diameter with my tape. Now, to change the diameter to a circumference, we have a little formula here that is C equals pi times d. Now, we've talked about pi before. Pi is a very important number when we're dealing with measurements of circles. In this case, we use a very simplified version of pi, just two digits after the decimal point, so it's 3.14. So for this example, I used To find my circumference, I took the 3.14 of pi and I multiplied it times a common diameter size that I saw when I was doing my drops, which was 2.2 centimeters. So if you multiply 3.14 times 2.2, you get a result about this wiggly equal sign, means the circumference is about 6.9 centimeters. So this is the sort of formula that you would use if you wanted to figure out how far you'd be walking around that Barringer crater. Thank you very much. Have a good day.